Welcome back. Again, I apologize for the second time in a row. Flight issues have caused us to go online, but I'm going to record this video, post it up on YouTube, and if you're watching this, then you already figured out all of this, so I don't know why I'm telling you again. But here we go. Let's dive into it. Excuse me. We're in 2.5, which is transformation of functions, right? So there are some functions that you should have a fairly good idea of what they look like. And I'll grab a couple. They are these. So you ought to know what these guys look like. The identity function is just that straight line. The square, x squared, is that parabola. The square root is just a kind of like the top half of a parabola that's been put on its side. Cube, right? The cube root looks like this guy right here. Just kind of comes up almost like a parabola from the bottom and then goes up almost like a parabola, but steeper on the right-hand side. Right. And then the cube root kind of does that sort of look, but rotated over. 1 over x, and then the absolute value of x. These guys, you should know what they look like. If you don't, there they are. But this is on page 134 of your book. You can just kind of glance at that if you need to. But what we're going to do is take a look at what happens when we change these just a little bit. So if I instead, let me zoom in here. I can't move anything now. There we go. If instead of just x, I have, say, x plus, oh, that's really big, 2, then that just moves up my graph so that I intercept at 2, and then I have that slope of 1 still. Pretend I can draw a straight line to save my life, but it's hard on this little, this is how big my pad is. It's very small. That's what it looks like. And what essentially has happened here is this graph has just been moved up 2 everywhere. Just take that graph, shift it up 2, right? The same thing would happen if I did, say, x squared, let's say -3, right? Well, if x is 0, that gives me a y value of -3. I can plug in values. If x is 1, that's 1 squared, which is just 1 minus 3, so that's at -2. And the same thing happens if x is -1. -1 gets squared to be +1, -3 becomes 2. And if we keep doing this, we're going to see that this graph essentially is the same graph that I can't draw to save my life. Again, you're going to get used to that. But everything's just been moved down by 3. Down by 3, down by 3, down by 3. Right? So it's just taking that graph, that parabola that we have, and just choop, 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 3 spots down, right? And if I do that anywhere, right? If I do, let's say, let's go to different color here. If I go the square root of x -4, I can take this entire square root of x function and just move it down by 4. 1, 2, 3, 4. And everything just appears the same. It's just been moved down by 4, right? So that's our first function. If I have, say, the graph of f of x, and that is just some function plus or minus some number, right? Then f of x is just g of x shifted up and down by a, right? It's shifted up if a is positive and down if a is negative, right? And if a is 0, then it's the same graph. It doesn't get shifted. Then f of x and g of x are the same thing, and it doesn't matter, right? So that's the first shift that we'll talk about, right? And so if we're asked to graph things in this Yeah, let's say we can graph, let's say f of x, and let's call it, I don't know, the x squared plus 8, right? Well, then I can say that this x squared right here is my g of x, right? Let g of x be x squared. And then my a is just 8. And if you know how to graph x squared, then you know how to graph x squared plus 8, because x squared plus 8 is just the graph of x squared shifted up by 8. And so we see, I'm going to put this down there. And so 1, 2, 3, 4, 5, 6, 7, 8. It starts there. It's a parabola, and it looks like that. Ish. Again, I apologize. It looks like a kindergartner's writing on here, but that's the best I can do, probably. All right. Let's go back up to this. I'm going to try to still this. Yeah, sweet. Again, we'll take a look at this. We're going to look at this x squared function for a second. If instead of x squared, I have y equals x minus 2 squared, right? And if I want to graph that, I can throw in some values, but I can see that if x is 2, right? Let's just get some x, y values. If x is 2, then I've got 2 minus 2 squared. But 2 minus 2 is 0, so that's 0 squared, and so this is 0, right? If I try, let's say, I don't know, let's say 1, then I've got 1 minus 2 squared. But 1 minus 2 is negative 1. Well, that's 1. Right? And let's throw in 3, and I have 3 minus 2 squared, but that's 1 squared, and that's 1. And if I graph these, I can see that I've got a point at 2, 0. So 1, 2, 0. And I've got a point at 1, 1, and then a point at 3, 1. So 1, 1, 3, 1. And if I grab more points, which I'll spare, you can do this on your own if you'd like, but you'll find that this thing essentially just becomes a parabola over here. Wow, that's ugly. That's not much better, but a little bit. And what's happened is that this thing has simply just been shifted to the right by, not surprisingly, 2, right? And that'll happen if I do this with anything. If I go like x minus 3 under a square root, so that whole thing's under the square root, then this whole thing gets shifted off to the right by 3, because it's going to take 3 input in for x to get a 0 under my square root. And so that happens here, and everything here has been shifted over by 3. Shifted to the right, shifted to the right, everything is shifted to the right. And that's the second type of transformation that we'll talk about here, is that if I have some g of x, let's say f of x is g of x, but shifted by some a inside the inside that parentheses, so it's not g of x, but it's g of x minus a, then this is f of x is simply g of x, shifted by a, right? And if a is positive, but noting that there's a minus in this formula, oops, that's not a highlight, right? If a is positive, meaning it's x minus some number, right, then it's a shift to the right. So for example, like x minus 3 squared, a is positive because it's minus 3, right? That is a shift to the right by 3. But if a is negative, then it's a shift to the left. So it's important to note that distinction. This would look like x plus 3. That means a is negative because it's x minus negative 3 to get x plus 3. And this is a shift to the left by 3. Excuse me. Okay. Let's take a look at a few of these. We'll graph some of these. let's graph, let's do something simple like x minus 5 squared, right? Again, if we just grab an XY chart, it can show us very quickly and easily y equals 5 is going to be that 0 point because 5 minus 5 is 0. And then when you square that, you still get 0, right? And so right off the bat, our graph that started out, oh my gosh, looking like this, has already been moved over so that it hits the y-axis at 5. So 1, 2, 3, 4, 5. It looks like that. And again, we don't really have to do point by point because it's going to be obvious that this thing still turns into a parabola and it's just been moved over. So this red part right here, it's looking hairy and ugly. The red graph, the red parabola is that x minus 5 squared. And again, the point of this is so that you don't have to do these charts anymore because those are time consuming. All you have to do is, oh, there's a shift, there's a horizontal shift, there's a vertical shift. I know how to do this. I don't have to take the time to point by point grab values. Okay. So let's look at, let's say, a little bit more. Let's say g of x is the square root of x plus 3 minus 3, right? So now I have two things going on. First and foremost, I should know that the square root function looks like that. Okay. But then I've got a minus 3, which means I'm going to shoot this thing down by 3, right? And then I've got this plus 3 inside the function, right? So when it's outside the function, it's plus or minus up and down with the sign. So if it's minus, it's going to go down. But if it's inside the function, as this negative or this 3 is, then it's against that function. So this is a shift to the left by 3, right? And if you want, you can decompose this. You can call this g of x is equal to this, h of x minus 3. But h of x, let's back up just a little bit, where h of x is just that square root function, right? But we've shifted it on the outside with a down by 3, and then we've shifted it on the inside, right in here, with a left by 3. And so that's all I need to know is from this graph, I can just go down 3, 1, 2, 3, and then also left 3. So it'll start here, and then I get that square root function, look, back out of it. And that's the graph of that function. Okay. Let's look at that. There we go. All right, let's look at this. The other thing that we want to look at when we're talking about these kind of things is a reflection. So a reflection is, say I take a graph, let's say we take x to the third. And if I flip that about the y-axis, right, then this is that function. And it's simply taking all of my x values and saying, now evaluate it at the opposite value. And what happens is then you end up with opposite x values ending up with those y values. And so it flips this thing about that y-axis, right? And so we can reflect simply by taking some f of x, which is equal to, let's say, g of negative x. f of x is g of x, but flipped about the y-axis. Right? So another one we can look at to demonstrate that is, let's say we have some f of x is equal to the square root of negative x, right? And so it should be clear here, we can't take the square root of a negative number, therefore x itself can't be a positive number because then it would be negative under the square root. But if x itself is negative, then negative x is a positive number, and then we're fine. And you can see then if we graph this, 0 is still fine because negative 0 is still 0, so I still get a point at 0. If x is negative 1, then I get negative 1 square rooted, and that's just the square root of 1, which is 1. And so if x is negative 1, then I have a value at 1. Likewise, we can argue, right, 4 is a good one. If x is negative 4, I have the square root of the opposite of negative 4, but that's the square root of 4, and that's 2. And so you can see all we've really done is flipped which x values work, right? None of the x values in the positive domain work. All of the ones in the negative ones do now. And so we've taken this square root of x and just flipped it about that y-axis. Another thing that we can do, let's take a look at f of x equals negative x squared. So you should know that x squared is that parabola that looks like this. But if it's negative x squared, then all of my values are going to be negative. So again, if I try some xy values, if x is 0, well, 0 squared is still 0. But if x is 1, negative 1 squared is negative 1. And if x is negative 1, the negative of negative 1 squared is still negative 1. And so you can see these values start to go off downward. Plug in 2, then I get negative 2 squared, which is negative 4. If I plug in negative 2, I get the opposite of negative 2 squared, which is still negative 4, because negative 2 squared is 4, and then this negative out here turns it back negative. And so I get these, and I get that parabola-looking thing. God, I'm bad at drawing. But that's what we're looking at, right? So then we would say that if f of x is negative of some function, then f of x is g of x, but flipped about that x-axis. Let's see, I want to do another one of those. We can do graph f of x is, I don't know, negative square root of x. Then, of course, square root of x looks like this. But if I'm going to negative it, all I have to do is know that this thing is going to flip about the x-axis. And so this blue one down here, this is the opposite of the root of x. Right? And that's all it takes. It's just that one quick flip. You can justify it by going through x and y charts if you want, but it will definitely turn into a flip like that. All right. If I have this function, say y equals 7x squared, what happens here? Well, again, I can plug in x and y values to kind of justify what we're going to say here. If x is 0, 7 times 0 squared is still 7 times 0, which is 0. But once I get to 1, then I have 7 times 1 squared. 1 squared is 1 times 7 is 7. -1, 7 times -1 squared is still 7, because -1 squared is still 1 times 7. And we get to 2, I think we'll see what's happening here. 2 squared is 4, multiplied by that by 7, and I get 28. And I think you'll see that on -2, you'll also get 28. So I still have this parabola. It's still an exponentially growing, it's a parabola, growth. But it's been stretched essentially by a factor of 7. And so I still have my point at 0, 0. But then I have a point at 1, 7. So there. And then a point at -1, 7. And then by the time we get to 2, we're way off the chart up there. And at -2, we're also way off the chart up there. And so I still have this parabola, but it's super thin. And it's super thin because every little bit, our old x squared would have landed us a point at 1, 1, but this has been stretched by a factor of 7. And the other parabola that would have had a value at 2 and 4, so like right there, has been stretched way all the way up by a factor of 7, all the way up to 28. So it's like Laffy Taffy, or those that old pink putty that you used to like put on newspaper and pull off, and you get the newspaper print on it. But it's like taking that and just stretching it by a factor of 7. And so we would say if f of x is something multiplied by some function, a times g of x, let's say, then f of x is g of x, but stretched vertically. And again, it's a stretch, meaning it's been like pulled and elongated if a is greater than 0, or sorry, a is greater than 1, right? But if a is less than 1, what's going to happen? Let's find out, right? Let's graph f of x equals, let's say 1/2 x squared, right? And I think it's not a difficult leap to see that everything is going to end up being half as big, right? If x is 0, 0 squared is still 0, so half of that's still 0. But if x is 1, then this is 1/2 of 1 squared. 1 squared is 1, so this is 1/2. -1, you're going to get the same value of 1/2. 2, I get 1/2 of 2 squared. 2 squared is 4, but half of that is 2. So I have a point at 2, 2. So again, it's not a difficult leap to see that I've still got that point at 0, 0. But the point that would be at 1, 1 is now at 1, 1/2. And the point that would normally be at 2, 4 is now at 2, 2. And so we've got, oh, that's not a great, but it's just going to be a wider, right? This right here is 1/2 x squared, whereas the original one, I've missed both, I realize that, but this is x squared. So everything's just been cut down in half. Whatever value this is, it's half of that. Whatever value this is, it's half of that. Okay. And so then that answers this question. What happens if a is less than 1? Well, then it is a compression or a shrink. And it just gets compressed by a factor of 1/2. And we also then might have something that looks like this. Let's say the square root of 2x. And this one's harder to see, but we can walk our way through it. And so if I get some x and y values here. If x is 0, clearly the square root of 2 times 0 is still the square root of 0, and that is 0. I'm not going to do 1. I'll show you why, because I'll do it. But that's the square root of 2 times 1, which is the square root of 2, which is, I don't know. I mean, I do. It's 1.414, but you don't need to know, right? But that's ugly, and I don't want to do it. So I'm going to pick convenient values. So I'm going to pick the 2. I'm just going to scratch that out because that's ugly, and I don't want to look at it. That if x is 2, then I have the square root of 2 times 2, which is the square root of 4, which is 2. And I can't do negative numbers still. So I'm going to move on to, I mean, 3 would give you 6. The square root of 6 is ugly. 4 is going to give you 8. The square root of 8 is kind of ugly. 5, 6 would give you 12. 8, though, I'm going to skip all the way to 8. Because that's 2 times 8, which is the square root of 16, which is 4, right? So I've got a couple of values, and I'll plot those. I've got the value here at 0, 0. So that doesn't change. 4, 5, 6, 7, 8. I've got the value here at 2, 2. So I get all the way to 2 before I hit 2. And then I get all the way to 8. 1, 2, 3, 4, 5, 6, 7, 8 before I get to 4. And so I get something that looks like this. Oh my goodness. Sort of like that. Right? And again, it's hard to tell what's happening here. So I'm going to graph on the same set of axes. G of x is the square root of x, right? And if I do an xy chart here, this one's easier. If x is 0, y is 0. If x is 1, y is 1. And I have to go to like all the way to 4 before I get the square root of a good, nice number, and that's 2. But these 3 are good enough. I'm going to graph these. I still have that point at 0, 0. But I have a point at 1, 1. And then I have a point at 4, 2. And so I get this sort of looking thing there. Now, what's happening here is oh, I don't want that to disappear. I hope I can get that back. Is a compression, but in the horizontal direction of 1/2. So this point here that was at 1, 2, 3, 4, 2 got squished all the way to half the x value to be 2, 2 here. This point here, the x value got cut in half, so everything got compressed towards the y-axis by a factor of 1/2, right? Which is a little bit different, right? We've got a nice whole number of 2 being multiplied in there, but that compresses stuff. And so we would say this. How do I get that thing back? Ah, there it is. Great. So we would say this. If f of x can be expressed as g of some number times x, right? Then you've got 2 things, just like the first one. It's either a compression, and this is a horizontal compression, by a factor, and we'll say compression of 1 over a, right? So that if let's say this, if a is greater than 0, right? But if it's not, then you have a stretch of still 1 over a if a is less than 0, right? So let's see one that has a stretch, perhaps. Let's say f of x is, I mean, the square root function works pretty well. Let's do, I'm going to stick with it because I like it. I'm going to say 1/3 root x, right? And again, we'll go x's, right? X, y, just to get an idea of what's going on. And we'll walk our way through why I'm picking the x values that I do. If x is 0, that's easy. 1/3 times 0 is still 0, and the square root of that is 0. But 1 is ugly, 2 is ugly, 3 is not too bad, because 1/3 of 3 is 1, and the square root of 1 is 1. But I'm going to get all the way up to like 27 before I get another good, nice number, right? Try them, because if x is 4, you get 1/3 of 4. If x is 5, you get 5/3. If x is 6, you get 6/3, which is just 2, which is still square root is ugly, irrational number. But if I get 27, then I have 1/3 of 27 under a square root. And that's the square root of 9, and that is 3, right? And so you can see how much further out in the x values I have to get in order to get nice, good y values. If I graph this, I have that point still at 0, 0. I have a point at 3, 1. And then I have to go all the way to, I'm going to call this 27 before I get to 3. Right, so you can see this thing is just being stretched. And I missed, but don't judge me. I just suck. But the root of x would have a point at 0, 0. And then a point at 1, 1. And then a point at 4, 2. And then so on and so on. So you can see that this thing would look like that. And everything's simply been stretched to the right by a factor of 3. If it was 1 here, it goes to 3. If it was 2 here, it goes all the way to 6, which is, again, my drawing is terrible. But that's what's happening, is everything is just stretched out to the right by a factor of 1 over 1/3, which is 3. Okay. In the end, let me just grab a homework problem here. Let's do this one, not too bad right there. And I mean like a problem from the book, not from your homework site. But let me grab, oops, not that. This, and we'll graph, wow, all right, that's helpful. Zoom out, you bastard. Zoom back in. All right, let's graph this. So there's two things going on. And first off, I have to know what 1 over x looks like. 1 over x looks like this. It has asymptotic behavior towards 0 and is negative on the left, and then asymptotic behavior on the right. So that's what 1 over x looks like. And so if I'm going to graph this thing, I've got to note first that this is going to be the graph shifted up by 2. And this x plus 3 means that it's going to shift to the left by 3. So this graph that I've just drawn up there is going to go up by 2. So this asymptote, there's an asymptote right here. 1 over x is asymptotic to both the x-axis and the y-axis. Those asymptotes move as well. So if my asymptote moves up by 2, I can just 1, 2, and I know I'm going to have an asymptote here, which I can just draw, lightly if you're in pencil. Don't go too crazy and put the darkest possible line ever. But I've also got the asymptote on the y-axis, and so that's going to get shifted left by 3. So 1, 2, 3. And that kind of gives us just our little carrying spot for these things. It's still going to be this upper right little, I don't know what you call that, but that little graph is going to asymptotically come off of the y-axis now, or the y-asymptote that's been shifted. And asymptotically approach the x-axis. And then the same thing down here, this guy simply asymptotically leaves the x-axis that's been shifted and approaches the shifted y asymptote. And so that's it. We've just taken this thing, shifted it left 3 and up by 2. Let me get one that's got a few in it, like there's not any that are terrible. Let me get this one. It's the ugliest one I can find. I don't know why it's got to mess with my Zoom just to copy and paste something in here. Okay, so we're going to do this one as well. So the underlying function here is the square root, and so we know that the square root of x looks like this-ish, right? And then I just need to know what's happening. This -1 on the inside here is a shift. Which direction is it? Take a second, try to guess, but that is to the right by 1 because it's inside the function itself. And then on the outside is being multiplied by -1/2. And so this is a shift, or sorry, not a shift, but a compression by 1/2. But it's a compression by a negative number. So that negative is going to flip it about the horizontal axis, right? And so let's just write this. It's a compression by 1/2, but then this negative is the third thing. We'll call it the third happening. That negative makes this thing flip or mirror about the x-axis. So there's 3 things that are happening here. And as long as I just take care of those 3 things, then that'll be the graph. So again, I'm going to put the original graph in blue. And by again, I mean now, not again. But the original graph looks like that, right? So I'm going to kind of work my way in, and I'll just do a couple of different graphs. So let's find purple here. I'm going to shift this thing right by 1 to take care of this. So right by 1 moves this thing to here. That gives me the square root of x minus 1. Right? And if I compress this by a half, I'll do that in green because that's been circled in green. So everything just gets kind of cut by half. That guy that goes down there, that guy goes down there. So it's, again, my artistic skills are lacking, but it's that purple thing squished, right? And then the very last thing that I have to do is take care of that negative. So let me write this. Green is the graph of 1/2 root of x minus 1. And then if I just flip this about the x-axis, that gives me the negative 1/2 root of x minus 1. Right. And so you'll see 5 or 6 things that happen in this graph, and it becomes super simple to graph. Whereas if I had just come to you yesterday and said, hey, graph -1/2 times the square root of x minus 1, you'd have been like, dude, why? I hate you. And you may think that today. That's okay. But it would be hard because you just have to pick out some values, pick out some x and y charts. But now, if you just know what the square root of x looks like, you just shift it right by 1, compress it by a half, and flip it, and you're done. You don't have to take 20 minutes to find an XY chart. Okay. All right, that wraps up section 2.5. I don't know what time I started, so I don't know how long we're into this. And there's no timer on my recording thing, so I'm just going to get through 2.6. But yeah, if you guys have questions, You know, I know the next time we meet on Monday is a test. I'm going to give you guys a practice test that you can go through. So to get you kind of prepared for that test. But between then and now, please email me. Please talk to me. If you have questions, ask. Get you guys squared away that way. But 2.6 is way up here. Is on variations and applications. So we have two types of well, we have a lot of types. We have two main types. The first is direct variation. And direct variation is when y varies. Essentially, I mean, it's silly to use directly in the definition, but directly as x does, right? So you'll see things like that. X varies directly with x or varies directly as x. But that means that y is just some multiple of x. Well, let's use k. They use k in the book. And so k is just it's called a parameter, meaning it's not a variable. It's not going to change like x and y do, but it'll have some value. And once you find that value for the problem, it's that value for that problem. It doesn't change. It's also called the constant of proportionality. Yeah, proportionality. Okay. But a question might be this. Okay. So we might have this question. They might give us some information. Y varies directly as x. If y is 20 when x is 5, find y when x is 4. So because it says it varies directly as x, I know that I've got y equals some constant of proportionality times x. But they give us more information. They tell us y is 20 when x is 5. So if y is 20 when x is 5, I can plug those two values in. And the only thing that I don't know now in this equation is what k is. But that's easy, because if I divide both sides by 5, then k is 20 divided by 5, which is 4. And so I know now that k has to be 4, and k is always 4 now through this problem. It's not going to be 4 in the next problem, but it's 4 for this problem. And so then they pose a question. What is y when x is 4? All right, I can figure that out because I know k is 4. And now if I'm plugging in, instead of x, 4, well, then I know that y is 16 when x is 4. Okay. So here's an application of that. Water melting from snow. The number of centimeters, denoted by W, of water produced from melting snow varies directly as S. And so since they tell us right there it varies directly, I know that my equation is that W varies directly as S. So I'm going to say that it's W equals K times S. And then they tell us some more information. The number of centimeters S is the number of centimeters of snow. Meteorologists have found that under certain conditions, 150 centimeters of snow will melt to 16.8 centimeters of water, right? And so that is a way of figuring out what the constant of proportionality is. 150 centimeters of snow is S. Make sure you get it put into the right variable. But that melts down to 16.8 centimeters of water. And so then I divide each side by 150 to figure out what K is. Cancels out on the left hand, leaving me K, and then that divides down to 0.112. So I know K. And then they come in and ask the question, how many centimeters of water, so how much water am I going to get, will 200 centimeters of snow melt to? Well, that is 200 centimeters of snow. I know my K is 0.112. And so I just multiply these two together, right? And that is not 0 point, but 224. .4. And so that's how much water we can expect 200 centimeters of snow to melt down to. The other type of variation is inverse variation. And inverse variation is when, like, if X rises, then Y decreases. And more specifically, according to this equation. So Y being inversely means that there's still this K, that proportionality constant, but that gets divided by X. And so you can see here, if X is larger, you have a larger denominator, which means this value of Y gets smaller. And the vice versa is true. If X gets smaller, you have a smaller denominator, and so Y increases. So we might be asked a question like this. If Y varies, and they can say either inversely or indirectly. Those two, not exactly synonymous, but a lot of books will use indirect variation. I don't like it so much. Typically inverse is what you see, but 2x or as x or whatnot. And then they say if Y is, let's say, I don't know, 10 when X is 2, find Y when X is 5. And we can. Once again, because it says inversely, right? And again, indirectly is not a great word. Some books use it. I don't think this book does, but inversely is what we want. Well, we know if Y is 10 when X is 2, that's a way to figure out K. So because it's inverse, I know I have Y equals K over X. But because Y is 10 when X is 2, I can multiply both sides by 2, and I found K pretty quickly is 20. Then also they want us to find Y when X is 5, so Y equals K, which I know is 20, divided by 5, and therefore is 4. So let's grab, not that one, I want this one. The time required to fill a swimming pool varies inversely. So right there, if it varies inversely, I know right off the bat that I've got an inverse relationship. But the time is t, and it varies inversely with the rate. So that is to say that I have t equals k over r. A tank truck can fill a pool in 90 minutes. So that is to say the amount of time that it takes to fill it is 90 at a rate of 1,500 liters per minute. So my rate is 1,500. But again, I can really quickly, just with that information, figure out what K is. That isolates K on the right-hand side, and I have that K is equal to, that's 135 and 1, 2, 3 zeros. So 135,000. But then the question is, how long does it take to fill it at that rate of 1,800? So I know that time is equal to this K, which I just found out is 135,000, divided by this 1,800 now is my new rate. Why is that not picking up? Oh no, you suck. Okay, timeout while my whiteboard figures out why it's being terrible. At any rate, you take that 135,000, it's divided by 1,800, and your answer is 75. Let me try to get my whiteboard back here. I think I just put too much on it, so it died on me. There we go. Just going to delete that. Bye-bye. And go new. There we go. All right, so we had the, at the end, I had the time is equal to the 135,000 divided by 1,800. And that division is just a quick calculation, it's 75. So it takes 75 minutes. Now, there's a couple of other ones that we would want to consider, and you might see them like written like this. Let's say y varies directly. Oh, wow. Square of x. Okay. So if y varies directly with the square of x, and we'll probably have more information. Let's say if y is 60 when x is 3, then find y when x is, let's say, 2. Right? And so we just have to be careful with the wording here. Y varies directly, so that means it's y equals k times x, but it's not x, it's with the square of x. And so it's y equals k times that x squared. So now we're varying directly with the square of x. And I can plug in information that was given. Y is 60 when x is 3. So 60 equals k times 3 squared. Or 60 equals k times 9. And so I'll divide each side by 9. 60 is not divisible by 9, but I can simplify that down to 20 over 3. And so I have that k is equal to 20 over 3. But I have k. And then I can come in and say, great, they gave us a question over here. Find y when x is 2. Well, if x is 2, then y equals k, which I know is 20 over 3, times 2 squared, or 20 over 3 times 4, or simply 80 over 3. And there's a few others. I won't go through these ones unless, I mean, if somebody asks me to, I certainly won't shy away from it. But they're not as common or interesting. But so here, if y varies directly with the nth power, so like we just did a square, then we get y equals k to the n. So in our case, we get y equals kx squared. If it varies inversely with the nth power, you would get simply that x to the nth power in that denominator. And then you might have a joint relationship. If it varies jointly with, say, x and z, then there's some proportionality constant multiplied by both x and z, right? There are some examples in the book. Throw it open to page 151 if you want to see those, but they're not a lot different than the ones that we've just done. Let me do one of the jointly ones, though. Let me see if I can find one so I don't have to make one up. That one there. There we go. There's one. And this is just from the book. I don't know why it's got to screw with my Zoom every time I paste something. All right, so here we have y varies jointly as x and z. So that first bit right there, y varies jointly with x and z, that tells me that I have the function y, or the equation y equals k times x times z. Okay. And I know this guy right here, if it tells me y is 56 when x is 7 and z is 8. Oh, they didn't ask a question. Well, we'll figure out what k is, right? Then we would say y is 56. That equals k times, I know x is 7 because it was given to me, and z is 8, right? And so 56 equals k times, well, 7 times 8 is 56. And so if I divide each side by 56, k is equal to 1. So any question they ask from the follow-up, they might say, find y when x is 3 and z is 5, right? But I know that since k is 1, then this isn't terribly difficult. It's just y equals that 1 multiplied by x multiplied by z, which is 5. Parable save there, 5. But 1 times 3 times 5 is 15. So again, if you have questions, please let me know. I'm going to be typing up a practice exam for you guys to play with. Today's Wednesday, right? Let me see. Yeah. Exam 1 is scheduled for Monday. Planning on that. And then, yeah, over the weekend, I'll get a practice quiz typed up and let you guys go through that. But in the meantime, let me know if you have questions, and I will see you guys on Monday. Thanks. Bye.